Now that we calculated the actual volume of the mixture, let's now move on to calculating the partial molar volumes of species 1 and species 2. Right? To do that, we'll have to use our definitions of the partial molar volumes, which is for V1 bar, it's just the partial derivative of the actual volume at constant temperature, pressure, and moles of N2 with respect to moles of N1. And then similarly for V2, let me clean up this line. We take the derivative with respect to N2. Okay? All right, and so there's actually different sort of strategies for calculating the V1 bar. One strategy we could take is we could literally plug in the expression we used here into this equation. That'll work, but as you could probably tell, because delta V mix, is a bit of a complicated equation, that could get really messy really quickly, right? But that method will work. But what I want to go over in this video is to actually show you a shortcut method. And the shortcut method actually comes from what was discussed when we previously went through how to analyze partial molar quantities based on a graphical analysis. Okay. And so here, from the graphical analysis, you may remember that we could describe the delta V mix using this relationship. Okay. Right? And so, this relationship, we derived it not really making any assumptions, right? So this was a sort of generic relationship. And as you notice in this relationship, we're relating delta V mix to the partial molar volume and other sorts of terms. And so essentially, what we could do is we could rearrange this equation so that we're solving just for V1 instead. Okay? So if I go to the next page, what we have is we could say V1 bar is equal to V1 molar, that's delta V mix, minus x2 d delta V mix dx2 x1 t p. Okay? And similarly, we could do the same thing for V2. Where we have V2 bar plus delta V mix minus x1 d delta V mix x1 constant x2 t and p. Okay? Right? And so we could use these two equations to actually calculate our partial molar quantities. Okay? But of course, we still need to take some derivatives in order to calculate V1 and V bar. So get V1 bar and V2 bar, we need these things. Okay? All right, so to get those derivatives, we need to take some derivatives. So let's go through that. Okay, so once again, our delta V mix expression was described like this. Okay. All right. as you can anticipate, we first need to take the derivative with respect to x2. So let's first rewrite all of the x1s in terms of x2, since it's a binary mixture. Okay? We could simplify this. Minus x2 squared alpha plus beta 1 minus 2x2. Okay. All right, and so now that we simplified it, we just take the derivative. And we get the following. Plus 2 squared minus 2 beta. Okay. All right. So now that we have this expression, let's just evaluate delta V mix at our mole fraction of species 2, which was 0.497. Okay? And if we plug in this into the x2 mole fractions, so let me make this more of a subscript. It's confusing. We get a value of 0.104 centimeter cubed per mole. Okay? All right. So, we evaluated that derivative and got a value for it. Let's now do the same thing, but now let's take the derivative with respect to x1. So, once again, here's our delta V mix. This time, let's rewrite x2 in terms of x1. Simplify. And then take the derivative. X1 minus 1 plus x1 minus x1 squared positive 2 beta. Okay? And then when we evaluate it, we find that we get negative 0.104 per mole. Right? And so as you'll notice, this derivative, when we evaluated it, ended up just being the equal in magnitude but opposite in sign to the other derivative. Right? And that makes sense, because here we're looking at a binary mixture, and when we think about changes in x2, anytime x2 gets larger, that means x1 must be getting smaller. Right? So there's a coupled relationship between x1 and x2. And so if we look at the derivative in terms of one of the mole fractions, the derivative in terms of the other mole fraction will just be the negative of it. Right? So that's also kind of another shortcut that you can think about. Okay? All right, in any case, now that we have those derivatives, we could now calculate our V1 bar. So I'll write it out here. So we have V1 molar and then we plug in our expression for delta V mix, or this is the derivative term, not delta V mix. All right, and we could do the same thing with V2. Alpha plus beta 2x1 minus 1 plus x1 plus x1 squared 2 beta. Okay. All right. So at the composition of our actual mixture, we get the following values for our partial molar derivatives. Okay. All right. And so we have these partial molar derivatives, and remember, these represent the effective volume of the molecules when they're actually inside the mixture, right? And what we could do is we can compare these values to the values of the pure molar volumes of the pure species, all right? So let me write those here again. And we see in both cases the partial molar volumes are less than that of the molar volumes of the pure species. And so consequently, that justifies why, or that explains why the total volume of the mixture is smaller than the molar volume of the ideal solution. Okay? All right, and so here, we kind of went through an exercise to actually calculate the partial molar volumes. Just to remind you about what I was discussing earlier when it came to the mole fraction derivatives. And so here, x1 plus x2 is 1. If you take the derivative of the left-hand side, you could distribute across the derivative, right? And if you took the derivative of the number 1, that would give you 0. And so consequently, dx1 is equal to negative dx2. So this is just a good shortcut to remember. Okay? All right, in any case, we went through quite a bit of tricky calculus and algebra in order to calculate these numbers. But in the end, we still need to check if our model is actually physically correct, right? If it's thermodynamically consistent. And so the way we would do that, I'll at least remind you. So check if model is thermodynamically consistent. So the way you would do that is you would see if it satisfies the 3 criterion, which is that at the limits of the model, so when x1 goes to 1, the equation for your partial molar volume would give you the pure molar volume. So this would be true for species 1 and species 2. The second criterion would be additivity. Right? Your molar volume of the total mixture, right? So not the ideal solution, but the actual molar volume, would just be equal to x1 V1 bar plus x2 V2 bar. So that has to be satisfied. And then the third criterion would be that the model needs to satisfy the Gibbs-Duhem relationship. Right? So here it would be, from the Gibbs-Duhem analysis at constant temperature and pressure, this would need to be true. dx1 plus x2 dv2 dx1, so be careful about that. Let me clean this up. Okay. All right, so you would plug in your V1 and V2 models into this expression, and then everything should cancel out to get you 0. So that would tell you that the models satisfy the Gibbs-Duhem relationship. Okay? And so, yeah, this is how these three criterion is how you determine that your partial molar volume models are thermodynamically consistent.